which actually resulted in the Facebook award for networking. However, Bill discovered that is not so much into network synthesis, although he still works on this topic, even he has a paper this year at NSDI, but he's actually more interested in programming languages and synthesis from that perspective. So I'm looking forward to hear his talk. Some work that you will see today are already published. Some are still under submission or preparation. So we will very much really appreciate your feedback. So thank you very much, Bill, for agreeing to give a talk, and we are looking forward to hear more. Thank you.
Sorry, got a notification that I was muted still. I didn't know how to do that without stopping sharing. Okay, thank you for the introduction. My name's Bill Hallahan. And I'll be speaking about counterexample guided inference of modular specifications. So really what this talk is about is how to use synthesis to make verification tools work better or make it easier to work with verification tools. And so I'm going to be showing programs in Haskell syntax. And so this is a map function, and it takes a function as input, and it takes a list and it gives us back a list. And the way it produces this list is it just applies the function to each element of the input list. We can give this function some specification. So we're naming the input list X's and the output list Y's. And then we're saying that the size of the input list should be equal to the size of the output list. And if we give this to a verifier, we expect that this property is true, and indeed the verifier will be able to tell us that this property is true. So more particularly, I'm going to be speaking about a class of verifiers called modular verifiers. And in particular, the code that I'm showing here is for a verifier called Liquid Haskell, but there's other modular verifiers you might be familiar with. So Daphne and ESC Java are also modular verifiers. And we can see what makes modular verification unique from this example. I have this add to function, and I'm saying that the output should be exactly 2 more than the input. And to implement add to, I'm calling a function named Inker twice. So let's look at Inker. Inker's specification says that its output is greater than its input, and it's implemented by calling, by just adding 1 to the input. So hopefully it seems believable to all of you that these specifications are true. And so you might expect, and because they're pretty simple, that if we gave this to a verifier, it would just say, yes, good, your code is correct. But in fact, modular verifiers don't look at functions definitions when trying to verify callers. They only look at specifications. And so what that means is that when a modular verifier is trying to prove that add to specification is correct, it won't see this whole picture. It will only see this piece of it. It will know that Inker's output is greater than its input, but it won't know anything else. And so because knowing that the output of Inker is greater than its input is not specific enough to know that the output of add to is exactly 2 more than the input, verification here will actually fail. And to get verification to succeed, we need a stronger specification on Inker that says that the output of Inker is exactly 1 more than its input. Now here, this example, it's a bit trivial. We can easily see, maybe why the specification is wrong. As we get to larger examples with more complicated functions and more complicated specifications, it becomes harder and harder to do this. So here we have this concat function that takes a list of A's, and it returns a list of A's. And it gets this list by just joining all of the lists in the list of lists together. And the specification we have says that if we sum up the sizes of all the lists in the input list of lists, that should be equal to the size of the output list. And to implement concat, we've made use of this append function that just takes 2 lists and appends the first list to the second list. If we gave this to our modular verifier as is, it's not going to be able to prove this property because we don't have any specification for app. And so in concat, the verifier is going to know nothing about what app is doing. So we could begin trying to write our own specification for app and trying to figure out what do we need to tell the verifier about app to get this to work. But that's a bit of a pain, and it becomes more and more of a pain as we scale to larger and larger programs. And so the question we're going to try to answer in this talk is, how can we automatically find the required specifications? Before I try to answer that, I want to step back a bit and talk briefly about some work that I previously did with my collaborators and that was published at PLDI 2019, because this previous work kind of led to our current work. And in this work, we were trying to answer a slightly different question. We weren't trying to automatically find specifications, but we were trying to help programmers working with modular verifiers debug the errors that the modular verifiers were getting them. And so the plan in this work was the user would take their code and their specifications and give them to the verifier, and hopefully the verifier just works right off the bat, and we know the code is verified. But if that doesn't happen, we had this separate tool named G2, and G2 is a symbolic execution engine that can produce two kinds of counterexamples to help explain why modular verification is failing. The first kind of counterexample is called a concrete counterexample. And this is just an input-output pair that satisfies the specification, but that causes a violation of the specification. And so this is what you might kind of traditionally think of as a counterexample. Abstract counterexamples are to help debug in the cases where the specifications are actually correct, but the verifier can't show that. And so what an abstract counterexample does is it points out a function that needs, or a function that likely needs a stronger specification and how that specification needs to be stronger. And I'll be showing some examples of abstract counterexamples in just a little bit. For now, though, I'll say what we noticed after writing this paper was we can maybe actually do one better. Rather than forcing the programmer to take abstract counterexamples and try to fix the code themselves, we can turn this into a CGIS loop. And when you get an abstract counterexample, you can give that to a synthesizer that will come up with a new specification. And then we can give that specification back to the verifier. And if we get a concrete counterexample to one of these synthesized specifications, we can also just give that to the synthesizer and tell it, use this concrete counterexample to fix the specification you came up with before. And so, as promised, I'm going to talk a bit more about what exactly abstract counterexamples and also concrete counterexamples are. And then I'll touch on how this whole loop works and show an example of that. And then I'll finish by talking a bit more about the synthesizer and specifically how we built a synthesizer for this problem using linear integer arithmetic, or define linear integer arithmetic specifications. So beginning by talking about counterexamples. As I said, we have two types. Concrete counterexamples are showing when the code is actually incorrect. So here I have that map function from before, except I've messed up the recursive case by just removing appending f of x. So this map function will always return an empty list. And the concrete counterexample here shows exactly that. If we apply this incorrect map to the identity and a list with 1 in it, we get an empty list back. Now, abstract counterexamples are helping us debug in the case of like the add to and anchor function that I showed before, where the code is correct, but specifications are too weak. And so here's what the abstract counterexample that we get looks like. It says that add 2 of 0 is equal to 3 if anchor of 0 is equal to 2. So the point here is the specification of anchor is not sufficient to tell us that anchor of 0 is not equal to 2. And so the modular verifier might think that anchor of 0 equals 2. And if the modular verifier thinks that anchor of 0 equals 2, then it will think that add 2 of 0 might equal 3. And so the way we have to fix this is strengthen the specification to tell on anchor to tell the modular verifier, no, anchor of 0 does not equal 2. So armed with these counterexamples, we can form a CGIS loop. And to demonstrate how this works, I'm going to go back to the concat append example that I had before. And of course, if we run the verifier on this, verification is not going to succeed. And so we can use G2 to get an abstract counterexample that helps explain why. And so this abstract counterexample says that if we call concat on a list with 2 empty lists in it, we might get the list 0, or list with 0 in it. if appending 2 empty lists gets us a list with 0 in it. And from this abstract counterexample, we can form a constraint that must hold on the specification for app. It must tell us that if the 2 inputs to app are both empty lists, then the post condition of app cannot allow the output to be a list with 0 in it. And we can actually just run app on 2 empty lists and see what it does. It gives us an empty list. And so this gives us another synthesis constraint telling us something that the specification for app must satisfy. It must allow an empty list to be returned. So if we give these constraints to a synthesizer, we can get a possible specification for app. And here the specification we came up with is that the size of the output list is always 0. Now, of course, this is not a correct specification. And so if we try to verify this, we'll fail. And then we can use G2 to get a concrete counterexample telling us, well, actually, if you append to a list with 0 in it and an empty list, you get a list with 0 in it. And this gets us another synthesis constraint. And again, we come up with a specification that's not quite correct. And so we keep on getting counterexamples. And eventually, if we continue this long enough, we'll come up with the specification that the size of the output list has to be equal to the size of the input list. The size of the output list has to be equal to the sum of the sizes of the input lists. And the verifier will be able to verify the code given this specification. So in some ways, this is a bit of a complicated example. We have a list, we have lists of lists, we have these functions that we're applying to lists. But it's also fairly simple in that it's really just 2 functions. It's concat and app. And in a real world program, you're going to have a much larger call graph with many more functions in it. And ideally, what we'd like programmers to be able to do is write down a single specification that kind of says, here's my high level intent for this whole module or this whole program. And then we'd like to come up with specifications for all of the other functions to be able to support this high level specification. And the way we're going to be able to do this is by splitting the call graph into levels. So the root of the call graph has level 1, and then every other functions level is its distance from the root. And the plan we're going to follow is we're going to walk down the call graph from level 1 to the lowest level. And at each level, we're going to try to come up with specifications for the level below that let us prove the specifications for the level above. So initially, we're going to say, OK, we have a specification for F. Let's come up with specifications for H and G that if those specifications are true, would let us prove the specification for F is true. And once we have those, we'll go to H and we'll say, OK, let's come up with specifications for the functions called by H that would let us prove the specification of H. And ideally, we'll just walk down the call graph once, and we'll come up with the correct specifications and verify the code. Now, of course, we don't live in a perfect world, so sometimes we might guess a specification that is incorrect. And in that case, we'll rely on backtracking. And we'll be able to know we have to backtrack in 2 cases. The first case is we might get a concrete counterexample that shows that some previous specification that we came up with is actually incorrect. In the second case is we might hit a point where the underlying synthesizer that's coming up with the specifications encounters a problem that's unrealizable. And in both of these cases, we backtrack. And the key point is when we backtrack, we always have a new constraint that prevents us from just retraversing the exact same set of specifications again. So in the case of a concrete counterexample being found, that new constraint just comes from the concrete counterexample. And when the synthesis problem becomes unrealizable, we rely on the synthesizer being able to produce an interpolant that explains why the problem was unrealizable. And we add that as a constraint. So now I'm going to talk a bit more about how this synthesizer actually works. In particular, how we built the synthesizer that synthesizes Leah specifications. So the synthesizer takes the constraints and the measures, which are these size and sum size functions that let us kind of access information about lists. But in general, they could also let us access information about other data structures. And it's going to produce either the result that the problem is realizable, and in that case will give us a specification, or it's going to produce a result that the problem is unrealizable and will give us an interpolant. And we're going to build the synthesizer using an SMT solver to synthesize these Lia constraints. And we want to make the job of the SMT solver as easy as possible. So we want it to only be having to deal with integers as inputs and outputs. But this poses a bit of a problem because, of course, as you've seen, we don't only have integers in our problems, we have lists, and we have these functions being applied to lists, and we have the ability to nest specifications inside lists. I'll show that in a second. And so we need to do some translation from these more complicated constraints into problems over just integers, and then we need to do a translation back. And so I'm going to focus on how we do these translations. So let's look at an example of a function. We have this function f that takes two integers and returns a list of ints. And all it does is adds 4 to both of the input integers and then sticks them in a list. So it's not a very complicated function. But there's 3 ways we can write specifications for this. We can write specifications that are directly applied to the integer literals that are inputs or outputs. So here we're saying that one of the integers has to be negative and one of the integers has to be positive. We can apply a measure to the list input. So we can say, for example, that the size of the list input has to be we can say that the list input has to be non-empty. Or we can talk about the contents of the list. So we can say that all of the integers in the list have to be greater than 0. So encoding integers that are already just integers into the synthesizer is not very interesting because the synthesizer deals with integers and the specification already just has integers. So I'm going to focus on how we deal with encoding these measures and ADT contents. So beginning with measures, let's look at some specific constraints. So here we're saying that if the precondition of f is satisfied by 0 and 1, the postcondition must be satisfied by 0, 1, and a list with 4 and 5 in it. And what's fortunate for us is that these constraints are always talking about concrete values. And so we can know that the size of the list for 5 is 2. So then when we give a constraint to the synthesizer, instead of giving it the list for 5, we can just give it the value 2. And when we get a solution that uses that input, we'll look something like postf xyz equals z greater than 0. And when we're translating that back into a specification, we just know that instead of having just z there, we need the size of z. To deal with finding specifications over the contents of lists, we introduce a new postcondition function that I'm calling postfcons here. And we'll use this in addition to postf. So postf is still encoding things about the size of the list, and postfcons is encoding things about the contents. So we say that postfcons has to hold on 0, 1, 4 and 0, 1, 5 because 4 and 5 are the contents of the list. And then if we come up with some solution that makes use of postfcons, so for example, that says that the return value has to be greater than 2 in both cases, we can again translate this into a specification just by sticking that inside the list to say apply this to the contents of the list. So to evaluate this, we ran our inference algorithm on 15 benchmarks, both created by us and drawn from a graduate student level class homework assignment. So here are running times for 14 of the benchmarks. All of the benchmarks involve 3 to 6 recursive functions. And the fact that the functions are recursive means that simpler techniques like just inlining would not be applicable to any of these benchmarks. The benchmark that I'm not showing here is significantly larger than all of the other benchmarks. It involves 34 functions and is the inner loop of a k-means implementation. We were able to prove that we're able to prove certain properties of this k-means implementation in about 596 seconds. So that's slightly under 10 minutes. So in conclusion, I've discussed our inference algorithm to come up with specifications for modular verifiers and how we built a synthesizer to find these specifications, find Leah specifications. Thank you, and I'm happy to take any questions.
Thank you, Bill. Let's start with the questions. Are there some questions with the audience? So, Bill, there is a question. Azadeh, do you want to just unmute yourself and ask, or if not, then I can read it. So the question says, what were the specifications for functions like map or reverse?
So
No problem.
the right, yes. So most of these are actually, the format of them was we had the map function or the reverse function, and then we had some property that we were trying to prove. So I don't remember exactly what the property was for map, but it would have been something like the length of the, it would have been something like the length of x's is equal to the length of map fx's. And similarly for reverse, it might have been something like x's, the length of reverse x's is equal to x length of x's, or maybe even just line reverse once. I can't, I don't remember exactly, but it was property functions about these underlying list functions.
Are there more questions? Let's see.
Bill, nice talk. Can I trouble you to go back to the slide where you talked about the going from layer K down to layer 1 and what happens there? It'll be easier for me to formulate my question. Yeah. So the specifications you synthesize for modules functions are specific to the user provided specification, right? Kind of tailored to that. And since you walk down the graph, so what can happen, right? You are starting from the user goal essentially, and it could happen that the specification, say for H or G or such, would be what, too abstract to prove the goal at the top level, and that then needs to be refined using the counterexamples. That's the idea.
Yes, exactly.
So how do you decompose the spec at level I to the lower level? What is the reasoning that could lead to specifications that are too abstract? I would assume. Yeah, sorry, go ahead.
No, go ahead. I'm not sure I completely understand the question.
So, well, you want to prove something at level 1, and you express that's your goal. You now express it in terms of sub-goals, right? The sub-goals are the levels 2 in this case. And as you create these sub-goals, they need to be strong enough to prove the original goal, right?
Yes.
So they cannot be too abstract.
Exactly.
So where can the specification then be wrong? I guess I'm missing where.
Yeah, I see. So the way the specification can be drawn is, so right at level 1, we're going to try to prove F, and so we're going to come up with specifications for H and G that let us prove the specification for F if these specifications are true. But we're only picking these specifications based on the counterexamples that we've seen so far. So it's possible that we'll come up with a specification for H or G that, if that specification was true, would let us prove F, but that specification isn't actually true. So for example, maybe to prove F, all we need to know is that H returns, or maybe to prove F, we come up with a specification that H returns numbers strictly greater than 0. And maybe there actually is some way that H can return 0. And so in that case, we'll have to backtrack and come up with a new specification for H that says that H can return numbers non-strictly greater than 0.
So the specification for H is then not created in this sort of deductive way where in order to prove something about F, I need the following thing about age. And if that is true, then I can prove things about F. It is essentially the spec for age is entirely data-driven and kind of bottom-up, right?
Well, I think it is definitely data-driven. I mean, so we only move on to trying to prove the spec for H once we know that the spec we have for H would be sufficient to prove the spec for F.
Mm-hmm.
So I kind of think of it as top down for that reason. But it is also true that we're not, I mean, we could learn new things and have to back up. We could learn new things about what each is doing and have to back up.
Okay, thank you.
I think you have the correct picture of how it works anyway.
Thank you, Bill. I appreciate the answer.
Let me see, are there more questions? Okay, let me just quickly, oh, sorry, there is a more question, excuse me. Supratik, would you like to comment or shall I read? Oh, sorry, no, that's Supratik answering his previous question. I'm sorry, it's not related to you, Bill. So let's then stop here. And maybe, okay, no, let's really stop here because so that we finish in time. And if you would like to know more, please contact Bill. He will gladly tell you more. Okay, thank you, everyone. Bye-bye.